So far we have learnt in detail the direct stiffness approach as applied to structures having prominent effect of the floor slab. So in the last few lectures we have learned how to assemble the total structural stiffness matrix also. The number of degrees of freedom will be less in this particular case and their numbering sequence is also different. The degrees of freedom shall be of two types, the joint degrees of freedom and the floor degrees of freedom. Let's now work further so as to understand the further computational procedures. So we begin with the bandwidth. For this particular example structure, the size of the KTS is 54 by 54 and that of KPP is 30 by 30. Let's try to find out the bandwidth. Let's say we have two typical members, one beam and one column. So these members we can think of for determining the bandwidth. Now coming to the beam member, let's find out the governing parameter x, which is the difference between the maximum and the minimum degrees of freedom connected by that particular member. So here for this particular member, the highest degree of freedom is 27, the one connected with the rotation of the floor, and the lowest degree of freedom is 1, which is the joint degree of freedom related to the vertical displacement at this particular joint. So for this particular member, x is coming out to be 27. Next, let's consider the vertical column here, and for this one, let's work out x. The largest degree of freedom is 30, which is again the floor degree of freedom, the floor rotation connected to the second floor, and the minimum degree of freedom is 1 connected to the vertical translation at this particular joint. So here the x is 30. So in fact, if we take other members also, we will find that the same results will get. The maximum value of x shall be 30. Hence the bandwidth for this particular problem is 30. So what we can find is that this is very large. So although this particular system, the way we are numbering and the way we are considering the degrees of freedom, we certainly have smaller matrix size because we have reduced degrees of freedom owing to the floor. However, the advantage runs out as far as the bandwidth is concerned. Now the bandwidth is typically here very large, and the reason for exceptionally large bandwidth is the connection between the floor degrees of freedom and the joint degrees of freedom. For example, this particular member, it has at its both ends the floor as well as the joint degrees of freedom, and there is a large number difference between the floor and the joint degrees of freedom. As such, we have the highest degree of freedom number 27 and the lowest degree of freedom number 1, and similarly for the other member we have the highest degree of freedom 30 and the lowest degree of freedom 1. So this interconnection between the floor and the joint degrees of freedom gives rise to large bandwidth. So let us try to revise our computational procedure so that we can get some kind of advantage as far as the bandwidth is concerned. Let us look into how this can be achieved. Now, in general, when we write the equations for the system of equations, so we have the force and the reactions vector. So P here consists of both the direct joint loads as well as the floor loads. So floor loads are considered at the reference points, and here we have UP and UX. UX are the displacements concerned with the reaction points. They are either 0 or have a fixed value. So here the total size of the KTS matrix we have already seen is 54 by 54, and when we see here the sizes, KPP is 30 by 30 and KXX is 24 by 24. Now when we look into KPP, we can find that KPP is made up of two types of elements. Some are contributed by the joint degrees of freedom and some others are contributed by the flow degrees of freedom. So based on this, the force vector P can also be partitioned into two parts. The parts made up of by the joint degrees of freedom and the flow degrees of freedom. And similarly, KPP itself can be partitioned such that we separate out the joint and the flow degrees of freedom. For example, here we can very easily see that the numbers from 1 to 24, they are all joint degrees of freedom, and from 25 to 30 are the flow degrees of freedom. So accordingly, we can split the displacement vector also into these subparts. So what we have done further partitioning of KPP. So KPP we have written in this particular form, and the sizes are like this. KJJ is 24 by 24 and KFF is 6 by 6. So accordingly, KJF will be 24 by 6 and KFJ will be 6 by 24. So now let's work out the bandwidth of KJJ. Rather than KPP, let's work out how much is the bandwidth of this particular matrix KJJ. Now when we do this, and we can just choose the same two members, the particular beam and the column. The main difference here would be that we are finding out the bandwidth of KJJ. Hence we are only considering the joint degrees of freedom and we are not considering the flow degrees of freedom at all. So for example, for the member marked star, which is the beam, so when we find out the parameter x, then the highest degree of freedom will be now 12. It will not be 27, but it will be 12, and the minimum degree of freedom is 1, so x is coming out to be 12. Similarly, for the vertical column member marked with sun, the value of x is 15 minus 1 plus 1. So 15 is considered because we are now considering the joint degrees of freedom. So 30 will not come into picture. So based on these, the higher of the two is 15. So the bandwidth of KJJ is 15. So what we find is that the talk of bandwidth does make sense in the case of KJJ, though it was not making any sense for KPP. Now with this, we can form our solution procedure. So now what we do, we keep KJJ as banded. So the procedure would be like this, that we first start with the top part of the equation, P equal to KPP into UP plus KPX into UX. UX are the prescribed displacements, often 0. If not 0, they have the set values. So we get here the modified force vector if Ux is not 0. If Ux is 0, then we simply have to solve P equal to KPP UP. So this method of solution is impractical, we have already seen, because the way KPP is organized. So we will follow another approach, because this will give rise to very large bandwidth, so computation will not be effective. So we follow the approach that we'll be considering now. So what we have done is that to take full advantage of the banded nature of KJJ, we make use of condensation. That is, we condense the stiffness matrix in terms of the flow degrees of freedom. And this has another advantage also, that being 3D structure, the size of the condensed stiffness matrix will be small, and this can also be used for dynamic analysis of the structure. So what we have done is that we have reorganized it like this. So this is our modified force vector. The modified force vector P star is split into two parts, Pj star and Pf star. And now when we have the equation, so we eliminate Uj from these. For this purpose, we use the previous set procedure of condensation that involves simple elimination. So what we do, we have the banded matrix Kj, and this also gives us the H. So J is the joint degrees of freedom and F the floor degrees of freedom. So how we can eliminate Uj? All we have to do is write these two equations. So from the first equation, we single out Uj and substitute in the other equation, that is number 2. So we get this kind of equation, and finally after manipulation we get a condensed force vector and a condensed stiffness matrix. So here KFF star is the condensed stiffness matrix, so it has been condensed in terms of the horizontal degrees of freedom of the structure, and then PF double star is the condensed force vector. Once we have these two, then the typical size of the system of equations to be solved is relatively small, and it can be very easily solved by Cholesky's approach. So we'll see now. However, this process of condensation means that we have to obtain the inverse of Kjj. If we see the expression, so this involves computing the inverse of Kjj, and Kjj is a large matrix. So here we'll see how we can use Cholesky's approach to find the inverse. So inverse basically means that if we multiply a matrix by its inverse, then the result is an identity matrix. So if we have A matrix and B its inverse, then the result is identity matrix. So to give you a hint how we can use Cholesky's approach, let's say I multiply this matrix A by the first column of this matrix B, which is the inverse. So what we get the first column of the final identity matrix, so that is this will be the vector. And similarly, if we are multiplying this matrix by the ith column of the inverse, then we get the ith column of the identity matrix, that is, so here we have 1 at the ith row and all other terms are 0. So this gives us a hint that if we are using Cholesky's algorithm, and if we have this kind of problem, that we have the matrix A and we have the end result this, such that we have 1 at the ith position, then solution of this by the Cholesky's approach will give us the ith column of the inverse. So using Cholesky's algorithm, we solve a problem A into x, where x is a vector equal to a vector with 1 at the ith row. So by definition, the solution will give us the ith column of the inverse of A. So all we have to do is we have to repeat this process for various values of I varying from 1 to n. So once we repeat this n number of times, we will get compilation of all the columns of the inverse. So this process we follow and we get the inverse of Kjj matrix. So now we can summarize our solution approach. So first of all, we have to obtain the inverse of Kjj by this process. Then after this, we find out the condensed force vector. Then we find out the condensed stiffness matrix. Then we solve the system of equations, the condensed force vector equal to the condensed stiffness matrix multiplied by the displacements of the flow degrees of freedom. So we solve this equation by the approach of Cholesky to obtain the floor displacements. So once we have the floor displacements, then we can make use of the relationship derived in the process of condensation to obtain the displacements corresponding to the joint degrees of freedom. Once we have all the displacements, both the floor as well as the joint related degrees of freedom, then we go to the member level and we use the code number approach, and for a particular member select the D star. So D star means these are the displacements of the member, but here the displacements corresponding to the flow degrees of freedom, they are referring to the reference point. Then we just make use of the displacement transformation matrix to convert these displacements into the absolute displacements, and once we have these, then we get the displacements in the local coordinate system, and finally we get the member end forces, and in this step we also superimpose the fixed ended forces if they are any. So this process gives us complete solution which includes the displacements as well as the member end forces. And the displacements, they refer to both the joint degrees of freedom as well as the flow degrees of freedom. So this is the complete process. What can we do if we are working with a standard software and we want to rigorously consider the slab action? For that purpose, there are two options. Option one is that if our software has plate elements, then we can include plate elements and we can model them, and this would rigorously include the action of the slab in the lateral load distribution. If the particular software does not have slab elements, then we can make use of these fixtures link elements. So these link elements which we introduce, they should be introduced at the floor level and they should have very high stiffness, so they should be incompressible so that they are able to fulfill the action of the floor slab. So this option is also equally fit to give us accurate solution. So with this we have finished now the treatment of the presence of the floor slab for lateral load distribution. Thank you very much.